fundamental theorem of calculus. Is that okay? Again, we know this one already, but still let me state that one because we need to observe something and we can compare. Again, that's what I did in case of gradient, am I right? I started with a single variable calculus. Again, single variable calculus that I'm quoting here. Okay, so I can compare it with a single variable calculus and I can generalize that one and all, am I right? In case of three variable, or that comparison will help us to remember actually. Is that okay? Now look at here. So if you want to do any integration from a to b, okay, in case of single variable calculus, okay, a to b f of x dx. So then what will you do? Again, we know that integration is a reverse process of differentiation, am I right? What we write a to b, we write df of x by dx, am I right? Into dx. That means we write this f of x as derivative of some other function, am I right? Is that okay? We are going to find what is the function whose derivative is this capital F of x, isn't it? We are going to substitute, isn't it? And now this answer is, we write like this, am I right? F of x, isn't it? Differentiation of integration, that should be f of x, that's from a to b, isn't it? And that is equal to f of b minus f of a. Is that okay? F of b minus f of a. Now let me just rub out this part, okay? Again, I just have shown like that, but let me just take this part. Integral of derivative, okay? Integral of derivative of a function, that's equal to function at the end point of this integral limit. So that is given by, again that is a difference of the function at the end point, but integral from a to b of a derivative of the function is it is equal to, okay, so function at the end point, am I right? Not equal to that is given by, okay, that is given by the function at the end point, isn't it? That's what you need to observe here. Okay, you have some function, you have taken derivative, then you are integrating, then the answer is function at your upper limit minus function at lower limit, isn't it? That means function at end point. So that's what you need to observe here. Can you note down that one? Observation. Integral of derivative is given by the value of the function at the end points. Given by the value of the function at the end points. The value of the function at the end point. So shall I keep it here somewhere? We call this as fundamental theorem of calculus, okay? Integral a to b, A and B are along x-axis, okay? So 2 points along x-axis, okay? df of x by dx into dx, that's equal to that's equal to f at b minus f at a, okay? Let me keep it here one side. Now let me go for three variable function. Again, let me define fundamental theorem of gradients. Okay, fundamental theorem of gradients. This is fundamental theorem of calculus in case of single variable calculus. Now let me go for three variable. Let me define three theorems here, three very important theorems here. The first one is fundamental theorem of gradient, okay, in case of three variable. So how we have started our discussion of gradient, do you remember? If you have any scalar field T, okay, so change in that scalar field, that's equal to gradient of the scalar field, isn't it? That's a vector. So dot product with dl vector over infinitesimal displacement vector. So see the expression carefully, isn't it? Again, you should be able to recall everything, am I right? If you move in a different direction, you will get different directional derivative and all, am I right? Just recall everything, okay, whatever we did with gradient, okay? Now look at here, let me take this part. Let me take this part, del t, gradient of t, okay, dot dl vector, okay? Gradient is a vector, am I right? Okay, gradient is a vector. You have taken dot product with the infinitesimal, what you call, so displacement vector, am I right? Now look at here, what I do is I will take a 2-point space, okay? So that is point A, that is noted by vector A, okay? So point B somewhere here, so whose position vector equal to B, is that okay? Point A and point B, whose position and vectors are A and B respectively. I will go from A to B in this kind of path. Is that okay? I will go from A to B in this kind of path, and what I do is I am going to take the derivative, okay? This is point A, I better to write nearby this point, okay? Point B, that means that is written by what you call position vector. I will go from A to B, okay, in some curved path, in some arbitrary path, okay, whatever the path you take, okay? And what I do is I am going to take line integral of this gradient of a scalar field. Can you see the board properly? I am going to take line integral, this gradient is a vector field, am I right? I am going to take line integral of this vector from A to B. Is that okay? Line integral of this vector, gradient vector, from A to B. Is that okay? Now, this is equal to, okay? So, this is equal, again, I have taken line integral of some vector field, okay? I have to specify the path, isn't it? To take any line integral, I have to specify the path. But look at here, this is equal to A to B. A and B are points in space, okay? A vector and B vector are points in space, okay? I mean, these are the position vector, whatever we have written, okay? This is equal to integral from A to B dt. So what is this one? That's infinitesimal change in the scalar field t, isn't it? Now look at here, what you are doing here, in this part you have done line integral, okay? When you see this part of the integral, okay? So that means when you go from A to B, this t is changing, am I right? You are adding that change of t, am I right? At each and every point of the line integral, you are just adding all of those changes, so that what is the total change in t, isn't it? Again, if you integrate from A to B, that meaning is what is the total change in t? So that total change in t, this is a change in t, am I right? Change in some scalar field t. So this is a total change in t. When you move from A to B, the total change in t is t at B minus t at A. Isn't it? So because A and B are 2 points, remember. Is that okay? So this is a total change in t, or it's like just writing what you call integral of differentiation. Is that okay? Just like this very similar to this one actually. Value of this scalar field at the end points of the integral. Okay. Now look at here what you got here. Integral A to B. Okay. Gradient of scalar field dot dl vector, that's equal to scalar field at B, okay, minus scalar field at A. Look at here. So this t at A vector means t is not a vector, okay. A vector stands for some x naught, y naught, z naught, okay. That means I am writing my scalar field some x naught, y naught, z naught. Is that okay? That is the meaning, okay. I am writing t at B vector means t at some position B, okay, t at some position A. So this is a vector, but this whole thing is a scalar. I hope you got that point. Is that okay? That means this one like this, okay. Yeah. Now look at this expression carefully. Look at this expression carefully. Right side of this expression, okay, right side of this expression is independent of the path taken from A to B. Isn't it? It depends only on A and B, am I right? Scalar field at A, scalar field at B. So subtract them. You got this one, am I right? Right side of the integral is independent of the path, am I right? Whatever the path you take, so this is the first path. You take some other path, isn't it? Second path, am I right? Whatever the path you take, this part of the integral remains the same, am I right? If initial and final points are same, then left hand part should be also independent of the path chosen, isn't it? So that's why we got one idea here, we got one rule here, okay, or we got one nature here. We got one nature here. Look at here. Whatever I have taken, what is T? T is any arbitrary scalar field, okay? I'm not specifying any special class of scalar field, okay? T is any scalar field. This is happening, isn't it? According to our what you call calculus idea, isn't it? Now look at here. So one thing you can note down here, look at here. So this integral of A to B del T dot dl, okay? This gradient of any scalar field, okay? I told this one yesterday, am I right? Gradient of any scalar field, okay? So this is a special class of vector field, okay? Whose line integral is always independent of the path. So can you note down that one? That's very important point. Whose line integral is independent of the path from A to B, depends only on endpoints A and B. Now look at here, what I do here is, I will make B equal to A. Is that okay? Is that clear? This is a special class of vector. You can take any scalar field. Once you take the gradient, that is a special class of vector field whose line integral is independent of the path from A to B. Then look at here, while writing the line integral of this gradient, gradient of a scalar, you don't have to specify the path. You can specify only endpoint. Because whatever the path you take in the line integral, you get the same answer, isn't it? So T at B minus T at A, isn't it? That's why for that special class of vector field, that means gradient of a scalar, you don't have to specify the path, you have to specify only endpoint, and you can define the line integral. But for most general vector field, okay, usually you have to specify the path, otherwise it looks like meaningless, am I right? Which path I have to take? If line integral is different for different path, then if you are not specifying the path in the line integral, that means it would be meaningless. But here, even though you are not specifying the path from A to B, okay, you can find the line integral, which depends only on the endpoints. Yeah, speak out. Wait a second, don't apply. See the mathematics first. Yeah, exactly. This is what we do in case of electrostatic, okay? Yeah. Now look at here, what I do is, the next step, I will make B equal to A. Okay, I will make B equal to A. That means I will start from here, I will go somewhere, and I will end here. Closed path, okay? So that means closed line integral of gradient of a scalar field dot dl. Is that okay? So that is equal to TB minus TA. If A equal to B, this will be 0, am I right? Look at the right hand side. If initial and final points are same, okay, if you have taken one closed loop, again you are ending at the same point, am I right? In that case, right hand side is 0, so that's why this closed line integral equal to 0. Can you grab that point? Is that okay? Around any closed path, okay, I have taken one of the closed path in space, okay, you can take any closed path that is 0, okay. So that's why one thing you need to remember, if you have a vector field, okay, if you have a vector field, if that line integral is independent of the path, then closed line integral will be 0. Is that okay? If you have a vector field whose line integral is independent of the path, okay, you can write that vector field in terms of gradient of some scalar actually. So let me extend this theorem later, okay? So then if you write that one as a gradient of scalar, you can write that line integral as what you call scalar at end points, okay? Differences of scalar field at end points. And again, if you make that end point same, that closed line integral will be 0. Are you getting this one or not? It's very important part. Is that okay? I hope by seeing just this part, okay, you can say closed line integral is 0, am I right? If you make A and B same. Now look at here, whatever I did, okay, I have taken arbitrary scalar field, okay? But once you take a gradient, that becomes a special class of vector field. Yeah, speak out.
So here our field does not take anything with us a conservative or non-conservative field.
No, wait. Don't go for that physics word. First, let us understand mathematics. Yeah, this kind of vector field is called as conservative field, okay? Because we are not physically assigning anything for this one, okay? I'm saying T is some scalar field, this is some vector field like that, okay? Later we shall talk about conservative field. Yeah, it is called as conservative field, okay? Now, shall we do one? Yeah, speak out. Now, to verify this one, shall we do one problem quickly? Unless we do some problem. Wait a second. Before getting into problem, let me write whatever the theorem we got. What is the theorem we got? Integral A to B. Earlier, A and B are 2 points on x-axis. Am I right? Now, A and B are 2 points in space, isn't it? So, gradient of a scalar dot dl vector, that's equal to that scalar at B vector minus that scalar at A vector. Can you find the similarity? Is that okay? Integral of some derivative that is given by the function that you have taken derivative at the end points. That value is given by the function at the end point. That's a scalar field here. Can you find the similarity? Speak out. Yeah. Now we shall quickly do one problem. Suppose let me take some scalar field as x into y square. Okay. Scalar field x y square. Now let me take two paths here. Okay. Let me take a plane. One here, two here. One here, two here. Okay. Let me take a point. What is this one? 2, 1. I will go from this path. That will, let me take it as a first path. Okay. I will take it as a first path. Okay. I don't know whether you can see this chalk or not. I'll take it as a first path. I'll take other one as a straight line. Second path. Is that okay? Other one is a straight line. And let me first take the gradient of this one quickly. What is the gradient? Quickly. X cap dou t by dou x plus y cap dou t by dou y. There is no z variables, isn't it? Dou t by dou z equal to 0. What is this one? Dou t by y square into x cap. Speak out. Plus 2xy into y cap. Am I right or not? 2xy into y cap. Speak out. Now I have to take that line integral along first path. Let me take the line integral from 0, 0 to 2, 1. Okay, I'll take this one as A, this one as B. Is that okay? Quickly do that line integral. Okay, do again along first path. Okay, along first path. If you go from here to here, okay, x-axis, y-axis. Okay, along this path. Okay, your x x is variable, y equal to 0. Okay, x is running from 0 to 2. Okay, dy equal to 0, but dx is non-zero. Am I right? Yeah, but first take so gradient of t dot dl. First find this one. Okay, what is this one? dl means dl means x cap dx plus y cap dy plus z cap dz. Am I right? Speak out. Speak out. When you take a dot product, you will get y square into dx plus 2xy into dy. Check this out. Y square dx, 2xy into dy. Now again, while doing the integral in this path, okay, dy equal to 0, this part is 0, okay, y equal to 0, that integral is 0, am I right? Along this path, integral is 0, you don't have to take that one. I am doing directly, okay. So from here to here, okay, along this direction, x is equal to 2, okay, dx is equal to 0, y is running from 0 to 1, dy is non-zero, okay. Dx equal to 0, dx equal to 0, only this part exists, okay. So 2xy, x equal to 2 into, y is variable, y dy, y varying from 0 to 1. What is this one? 4 y square by 2, 0 to 1, is equal to 2. Check this out. So that's why total line integral along the first path, okay, total line integral along the first path from A to B, okay, along first path, so of your gradient of t dot dl, that's equal to 2. That's what I got. Am I right? Speak out for first path. Let me go for second path quickly. Second path. Write the equation of this one, the straight line. What is the equation? Y equal to 2 or 1 by 2? 1 by 2x. Half is the slope, am I right? 1 by 2 into x, am I right? dy is equal to half dx, am I right? Now substitute that one. What was that one? Gradient dot dl, that's equal to, what was this one? Y square dx plus 2xy dy, am I right? So substitute this one. Write everything in terms of x. What is y square? X square by 4 dx, am I right? Plus 2x into, what is y? X by 2. dy is again dx by 2. Isn't it? Now the 2 got cancelled. Then you can integrate. What is the, how x varies when you go along this line? X varies from 0 to 2, am I right? 0 to 2, x square by 4 dx plus x square by 2 dx. Check this out. What is x square by 4 plus x square by 2? Speak out. Or just do this integral quickly, tell me. Three x square by 4. Three by 4 integral 0 to 2 x square dx. Check this out. Am I right or not? Anyone? Are you doing parallelly? Speak out.
Yes, sir.
Now 3 by 4 x cube by 3 running from 0 to 2. 2 cube is 8. 3 got cancelled. 8 by 4 2 again. Okay. I mean, this will happen for any scalar field, whatever you take, okay? Any differentiable scalar field, okay? And obviously, if you have taken what you call closed line integral, okay, along this line integral, you would have got 2. When you take, if you want to take closed line integral, you have to reverse this one, second one, am I right? That means you have to replace dl by minus dl. So then this would be minus 2, so that closed line integral will be 0, isn't it? Check that out. How closed line integral will become 0, okay? Is that clear? So this is, yeah, speak out.
Sir, your coordinates were given, sir.
Here?
Coordinates were given.
No, not only coordinate. Yeah, it is given. It is given. You have to take from point A to point B. That's what I have taken.
Sir, these coordinates were given now, sir?
Yeah, they will give that one. Okay, otherwise, how do you, again, if endpoints are not given, then also it is meaningless. Okay. Very similar thing will come in the complex analysis, but that mathematics target is different. Okay, here we are going to use this one for a real electric field, real quantities, isn't it? I mean, in our application. So this is a real, what you call, analysis. I mean, how to say, real, real variable calculus. Okay, not complex. We apply so that again where our t is also real, everything is real here. Okay, but very similar mathematics comes in case of complex analysis. But there, here it can be extended to 3 dimension. Am I right? X, Y, Z, isn't it? Here I have taken path in a 2 dimension, so that it's quite simple. Okay, you do the problem from Griffiths where he has taken many paths in the 3 dimension. Okay, but what I'm saying is, if in what you call complex analysis, you find similar mathematics, line integral. Okay, so there, if the function is analytic, closed what you call contour integral is 0. This kind of idea comes. But there it's a complex plane. Okay, your path will be on a plane. Here path will be on a space. Okay, I mean both has a different target. Okay, both mathematics has a different target. Okay, yes. Now, fundamental theorem of gradient. So that I kept here. Okay, let me keep it here. Now let me go for fundamental theorem of divergences. Fundamental theorem of divergences. Look at here. How did I define divergence? Any idea? Volume tends to 0, 1 by volume into closed surface integral of V bar dot dA vector. Am I right? Volume density of the outward flux, isn't it? That's how we define gradient. Am I right? Now look at here. What I do here is, so when volume tends to 0, this flux also usually tends to 0, very small. Am I right? Speak out. Now what I will write is, I will write this one as some d phi divided by dv volume. Not d phi actually. D phi looks like change in phi. Am I right? I don't know. D phi looks like change in phi. I'm not talking about change in phi. I'm talking about flux. Some flux. Okay. Some amount of flux. This is amount of flux. Am I right? Not change in flux. This is not a derivative. Okay, this limit is not a derivative. A return point. You can't write like this. What you can write is, how do you write amount of flux? But this will be dv actually. The denominator, when v tends to 0, this will be elementary what you call volume actually. Are you getting my point? Speak out. See the equation properly. Okay, think with me. So this will be dv. Okay, what I shall write the numerator? What I shall write?
Flux density is there, right?
No, that is a total is flux density. Okay, over a point again. When you take a point in space, you can take an infinitesimal volume around that point, and you can find outward flux. Okay, and you can divide by volume. So that's the outward flux density. Is that okay? Now look at it. Yeah, let it be. Okay, we shall see that one. Now look at here. So try to grab this logic, okay, so that you don't have to prove that one. You can logically prove that one. Okay, you have some vector field in space. Okay, it may have sources again at different position. Is that okay? See here. Now what I do is, I'm going to take what you call one cube here, because cube is quite simple to work with, isn't it? Let me take a cube here. Small cube. Okay, later I will make it as an infinitesimal cube. Okay, now later I will shrink this volume. Okay, I'll find outward flux. While finding outward flux, what you do, you take dA vector like this. Speak out. Isn't it? No, actually I want to shrink that one to d2. Okay, let me draw bigger. Later I will shrink that one. Is that okay? First let me explain the logic. Okay. Is that okay? Let me take one cube, okay? Let me find what you call volume density of the outward flux. I mean to find density, it should be very small, okay? To find density is defined at some point, isn't it? But what I do, I'll take flux per volume, okay? This has some volume V, this has some volume V. I'll find total flux of the vector field V, okay? In space, you have vector field V, okay? I haven't taken that one, okay? In space, you have vector field V, everywhere. I will take what you call surface integral of this vector field, okay? So over this what you call closed surface, this is a cube, okay? It has a closed surface, okay? Now again, let me concentrate again. How do you take dA vector? You take dA vector like this, am I right? You have you done problem properly yesterday? So again, here you take dA vector like this, dA vector like this. Here you take dA vector like this, am I right? Like that you take the surface integral, am I right? Now look at here, what I do is, I'm going to add, again, I calculated this one, I'm going to divide by volume, okay? I'm going to divide by volume. Now what I do is, I will multiply this one with the volume, okay? Speak out. So this was kind of density, am I right, per unit volume. Now then, if I multiply that one with the volume, again, so then what will happen? Again, this will happen to be this one, am I right? Again, this volume term will get cancelled, am I right? If I multiply with the volume, okay? So let me write divide by V, I'll multiply with the volume. Is that okay? I'll call that one as S1. Is that okay? S1, this is first surface, okay? Now what I do is, I will take one more what you call very similar cube, adjacent to this one, attach to this one. Is that okay? One more cube attached to this one, like this. Can you imagine? Now I will take, let me take this one as what you call V1, okay? V1. This total surface, I will call it as S1, okay? I will call this one as V2, okay? Let me take V1 equal to V2. This whole surface, this closed surface for this volume V2, I will call it as S2, okay? S2 is also closed surface, okay? While doing the surface integral S2, okay? Okay, here you take dA vector like this, okay? Here you take dA vector like this. What would you take dA vector here, which surface is common for both, okay? That you take dA vector here, isn't it? Speak out. Speak out. That's why flux contribution by this one and this one will cancel out when you add that one, when you add the flux. Look at here. Wait a second. Are you getting a point? For this cube, you take dA vector here. For this cube, you take dA vector here on this what you call common surface. Am I right? So that's why what will happen is, what I do is, for this volume V2, again I do surface integral S2, okay, close the surface integral V bar dot dA bar, okay. So divide by V2, okay. This was what you call density, and I will again multiply by, pick out, V2. Now what is the result? What is the result? Tell me. What is the result? Tell me. Again, these volumes will get cancelled, okay? These volumes will get cancelled. Now again, you have added two surface integral. For one is S1, other one is S2. Am I right? Now when you added those two surface integral, okay. Now the net effect is, look at here. So this part of the surface integral got cancelled. Only this part, behind part, those are what you call added up, okay. So that is equal to surface integral of a vector field, okay, over the surface of volume V1 plus V2. Let me define like this. So this is equal to, okay, so this is equal to surface integral, where the surface is a what you call boundary of volume V1 plus V2 of what you call V bar dot dA bar. Are you grabbing this logic or not? Tell me. Is that okay? So now what happened is, as a effect, okay, look at here, you can just rub out this middle part, isn't it? Because that part of the surface integral cancelled out each other. The effect is, okay, the effect is, look at here, surface integral of V1 plus V2. What is the volume? V1 plus V2. Isn't it? Surface integrals over this common what you call surface that got cancelled because of the opposite dA vector. Isn't it? Are you grabbing this logic? Speak out, someone. Where surface is surface of the volume V1 plus V2. Can I say like this? This whole surface?
S1 by S2.
No, the total surface will not be S1 plus S2. This common part is removed, am I right? Total surface will not be S1 plus S2. Volume will add. Speak out.
Okay, I mean that
Because this middle part is removed, am I? Total surface will not add, isn't it? S1 means I was talking, S1 was the, what you call, surface of cube V1, okay? S2 was the surface of cube V2.
then there is no left S1 and S2.
Again, total surface happened. Don't write S1 and S1 plus S2, but you can add V1 plus V2 and you can define a volume V. Now let me define a what you call surface S. Speak out. So shall I move on with this logic? Now what I do is, I need some more space. I have a what you call volume, okay? I have a volume. I have vector field, okay? I will take a what you call infinitesimal volume element, okay? So I'll find divergence of a vector field, okay? Okay, I'll find divergence of a vector field at that point. And I will multiply that one by d2, volume of that infinitesimal volume element. Okay, now look at here. So divergence of volume density of the flux, am I right? So now you can take this small v into this part, isn't it? So can I just write like this? So this is very small surface integral, okay? Surface integral of, okay, let me draw like this. I think, yeah, this is the right word, okay? So what I can do here is, okay, this whole thing I can write like, since volume is very small, I can write like this. This surface also very small, okay? Very small closed surface around that point, v bar dot dA bar. So divide by dv, infinitesimal volume element, or let me call it as d tau. Is that okay? D tau volume element. I'll call it as volume element. So that's equal to del dot v, okay, where this S is the surface of this volume, okay, this small infinitesimal volume, okay. Now what I do is I will take this d tau here. Then what you get here? You get what you call surface integral over this volume. Am I right? Of v bar dot dA bar. Is that okay? Now what I do is I am going to add similar infinitesimal volume, okay. Then what will happen? Del dot v into d tau 1 plus del dot v into d tau 2. Am I right? So as a result, okay, you have to add that surface integral. Am I right? I have shown what happens when you add the surface integral here. What will happen? So that will be the what you call surface integral of v bar dot dA bar, where now this surface, this new surface is the surface of d tau 1 plus d tau 2. Am I right? Isn't it? Like that, I am going to continue and I am going to what you call span the whole region of the volume. Is that okay? And I will make this d tau very, very small. Is that okay? Okay, don't write S equal to, S corresponds to actually, okay? S corresponds to volume d tau 1 plus d tau 2, okay? Like that, I am going to span the what you call total surface, okay? Now look at here. When you do like this, okay? If you add what you call one more surface, let me draw it here bigger, okay? Is that okay? So again, so this part was vanished, am I right? So later what I do, I'm going to add what you call my surface above. Is that okay? Let me take it like this. Then these what you call interface effect also vanished, isn't it? As a total, you will have what you call flux through the, I mean, again, whenever you keep on adding this kind of cubes, okay, the net surface integral will be surface integral of the total surface of the total region. Are you getting my point? That's what happened earlier, isn't it? Just generalize that one. When you keep on adding this kind of cube, you will generate a net volume, isn't it? Net flux will be, again, you are going to add fluxes also, am I right? Net flux will be flux of flux through the what you call the final region, am I right? Speak out. Again, these interface effects will be cancelled out, isn't it? Speak out. Can I just rub it out? Isn't it? This interface effect will be cancelled out. Ultimately, you will get what you call flux through this surface actually. Can you imagine this surface? Is that okay? You had 4 cube over there. Is that okay?
Sir, I mean, how do I know these 4 cubes or 5 cubes or how many cubes are there?
No,
Because I am seeing from the outside, right?
No, not like that. Here you later again first take the logic, then we will shrink that one to infinitesimal, so that we what you call we just go through the what you call we just span this region. Is that okay? We just go through each and every point. No. Again, you are not what you call keep this result in mind. Okay, we have taken 2 cubes. Okay, we have taken flux due to surface of this cube, flux due to surface of this cube. Okay, then what we got, the what you call the, again when we added that flux, okay, this interface part of the flux was what you call cancelled out. Am I right? Now when you added that surface integral, okay, you got surface integral of this total part. Am I right? Are you getting a point? 2 cubes together. Wait a second. So now similarly, add one more cube, one more what you call cuboid here. Is that okay? Then again do the surface integral of this one and this one. Is that okay? Then in this inter part, in this interface part, okay, due to this cube, while finding the surface integral of this cube, above cube, you will take dA vector here. While finding the surface integral of below cube, you will find dA vector here. So that again that interface, I mean the contribution by this interface is also vanished. Isn't it? Then the net what you call surface integral will be surface integral of this part. Look at the diagram how it happened. Am I right? It is getting bigger, isn't it? So that's why I'm going to generate cubes like this. Okay, I'm going to generate cubes like this. So when I generate what you call cube like this, what will happen is, so now the define, so 1 2 3 4. Okay, so d to 1 plus d to 2 plus d to 3 plus d to 4. Okay, define the volume. Okay, this volume. Now take the surface. Okay, and that will be the surface integral, that whatever we have written. Is that okay? Speak out. Let me just write this. So del dot v d to 1 plus del dot v d to 2 plus del dot v d to 3 plus del dot v d to 4. Okay, and again this del dot v d to, that I have written like this. Am I right? Del dot v d to, del dot v d to, that will be equal to surface integral, but that surface integral corresponds to this volume, infinitesimal volume, okay, of v bar dot dA bar, isn't it? Now I am adding this left hand side, okay, for different surface. I have to add surface integral. When I add the surface integral, okay, according to previous logic, okay, I will get a surface integral, okay, I will get a surface integral for the volume d to 1 plus d to 2 plus d to 3 plus d to 4, isn't it? Speak out. This is the logic that I want to convey. Is that okay? Now, so that is equal to V bar dot dA bar. Like this, what I do is I am going to span the whole region of this big volume. Okay, arbitrary shape. It can be arbitrary shape. Okay, because we will make this one infinitesimal. Is that okay? So then what will happen is, again, if you make this d toes are very small, this will become an integral. Okay, and the result is surface integral of the total volume, of the total surface, end points of the volume. Is that okay? So what we do is we take an integral, okay, of del dot V, because these are infinitesimal, am I right? d2, okay, over this volume V. V you can write d2 plus d2 like that, okay. So that is equal to, okay, are you getting a point? So take it as a cube and infinitesimal cube and just add that up. Is that okay? Speak out. So then what is the result? So this interface of the cube, or what you call common surfaces of the cube, that contribution will cancels out. At the end, only surface contribution, total surface, total volume, and total volume surface of the total volume contribution will remain for the flux, isn't it? No, the surface which encloses the volume, that surface integral will remain. Just take the earlier logic again, you will understand. Wait a second. So closed surface integral, the surface is corresponds to volume, this volume V. Is that okay? Closed surface integral of V bar dot dA bar. Speak out.
So when we remove the phases, sir, then sir, we can say that we are now we are integrating the sir a bigger cube, sir.
I mean we have added that volume region, am I right? We have added that volume region and the new volume happened, and I have shown the surface integral. When you add similarly surface integral, that is the surface integral corresponds to new volume, that common surface integral got cancelled out each other, isn't it?
There's a new volume also will be the volume of the cube, sir, a bigger cube, sir.
Bigger cube. Like that, you start generating the cube, infinitesimal cube, so that even though the total surface is kind of weird shaped, okay, so you can just generate that one. Is that okay? Don't take big cube. These are infinitesimal cube, because so this divergence, again this d2 whatever I have taken, this is infinitesimal cube, infinitesimal volume element. Is that okay?
So sir, we with taking the infinitesimal cube, sir, we want to extend the whole surface, sir.
Yeah, again we are just building that up. We are just building that cube so that it covers the whole volume. And simultaneously, when you take the divergence, when you multiply by d2, you are getting the surface integral over each small cube. When you add those surface integral, so the effect of the surface integral in the interface of cubes, okay, that will cancel out, so that only total surface integral of the total volume remains. So that's why I have written like this. Is this logic okay?
Okay, sir.
Yeah. Grab this one. Is that okay? Take this one. Yes. Yeah. Again, write down this one and just generalize that one. Is that okay? Speak out. Yeah. Now we call this one as, look at here, fundamental theorem of divergences. Okay. Closed volume integral of a divergence of the vector field throughout the volume. Okay. You have to do the volume integral. This is a scalar field. Am I right? So that's equal to surface integral of the vector field over the surface which encloses that volume. Okay. Now look at it. If you have any volume, okay, what is the end point of the volume? That is a surface. Am I right? Now look at here. Let me place it here. Let me place this theorem here. Volume integral of, okay, divergence of vector field That's equal to closed surface integral of V bar dot dA bar. Can you now compare again? Integral of some derivative that's equal to value of that one at the end point. End point of this volume is a surface, closed surface. Can you compare? Very easy to remember. Is that okay?
So please speak a statement, sir. Statement.
No, I mean, it's just a comparison. Again, that's what I told, am I right? That integration of derivative is given by value of the function at the end point, am I right? That's the statement I have given. So we are just comparing one by one here. Here it was a path. Again, value of the function at the end point. Here it is a volume. What is the end point of volume? That's a closed surface, okay? It's a surface integral. Now let me take one example, okay? I have a vector field, okay? I have a vector field V is equal to y square x cap, okay? Plus 2xy plus 2xy plus z square y cap plus z square y cap, okay? Plus 2yz z cap plus 2yz z cap. Is that okay? So now let me take that what you call closed surface integral directly, okay? So the surface that is what you call cube, okay, which with one corner at the origin. Okay, let me take a cube. X, Y, Z, okay? So 1, 1, 1 here, okay? Cube of side 1, whose one of the corner is at the origin, okay? Now let me directly take the surface integral, because yesterday I explained how to do the surface integral, am I right? How to take dA vector and all, am I right? I hope you can deal with that one, okay? Do the surface integral. Closed surface integral of this vector field, okay? So this will give the value 2 here. This is the vector field, this is the surface, okay? This will give the value 2, okay? That is the right hand side of the theorem, am I right? Right hand side of this statement. Now find the left hand side. Because for cube I told it's very easy to find the volume integral 0 to 1, 0 to 1, 0 to 1, isn't it? Your integral limit. Quickly do that one. Find the divergence. Find the divergence. Dou Vx by dou x plus dou Vy by dou y plus dou Vz by dou z, dou Vx by dou x 0, dou Vy by dou y 2x plus dou Vz by dou z plus 2y is equal to 2 into x plus y. Speak out. Now volume integral of that one, that means del dot v, okay? Actually we write only one integral symbol, but d tau, when you expand d tau, which is dx, dy, dz, isn't it? It's a 3 integral actually. So dx, dy, dz, okay? To span this cubical region, okay, you have to make 0 to 1, 0 to 1, 0 to 1 for cubic, okay? For prism shaped it was different, isn't it? Just work out that problem. Now this is equal to 2 into x plus y. Can you quickly do? 0 to 1 x plus y dx. It is like this. 0 to 1 dy. Because here y variable come. Again, z variable is not there. You can take 0 to 1 dz. That's equal to 1. X plus y dx. Quickly do that one. You have to do it like this. I hope you know how to do that triple integral. 0 to 1 x plus y dx. X square by 2 plus y into x running from x equal to 0 to x equal to 1, isn't it? Then integral 0 to 1 dy dz part is 1. Any mistakes? Wait. Any mistakes here in this step?
Sir,
2 is coming. 1 by 2, this is 1 by 2 plus y into 1, am I right, when you substitute x. So again you have to integrate 0 to 1 dy, isn't it? So that's equal to half into y running from 0 to 1 plus y square by 2 running from 0 to 1. Is that 2? Half plus y dy, isn't it, is equal to where is the mistake?
Sir, 2x plus 1.
Okay. Outside one more 2 was there, am I right? That 2 I left out. Yeah, this 2 I left. Yeah, it will give the 2. Okay, practice this one. I hope you got how to deal with this integral. Okay, how to deal with this integral. So once x and y integrals are done, what will happen? This will become a constant. You can take it outside. You can take you can do 0 to 1 dz separately. If any z variable is there, take it inside. Okay, take that whole term inside. You can write like this. Okay, some scalar field. Okay, dx. Okay, you can do dx integral first. Okay, so then you can put a bracket. Then you can do dy and you can put a bracket. Okay, then take the whole thing and you can do dz. Okay, this is 0 to x1. Okay, 0 to x1 to x2. Okay, along x-axis. Okay, y1 to y2, y variable, z1 to z2. Okay, this is how you can do the volume integral. Put the bracket properly, you will understand. Is it okay? Yeah. Now look at here. Shall I move on? Now this list is getting bigger. Is that okay? That list is getting bigger. Now look at here. Let me give the similar logic here. How did we define that? What was the curl? It is at 8:30. I know. I know that. You don't worry. Yeah. How did I define curl of a vector field del cross v dot del cross v dot n cap? Am I right? That's equal to limit some area tends to 0, 1 by mod of area vector. Then closed circulation of the vector field v bar dot dl bar, where that circulation is taken over the what you call boundary of the area. Am I right? That area. Or what I can do here is, if I take this area very, very small, okay, so this is the path integral over that small area, circulation v bar dot dl bar divided by dA infinitesimal area, because I made limit area tends to 0, isn't it? Then I can take this dA here, isn't it? I can take this dA here, I can write del cross v, okay, dot n cap into dA, that will become dA vector actually. N cap into dA. N cap is was perpendicular to the surface. That's equal to closed integral of v bar dot dl bar. Now right hand thumb rule should be used to fix this dA or n cap, isn't it? If circulation is taken over the direction of the finger, okay, thumb will represent n cap direction of dA vector direction, okay, where dA vector is equal to dA into n cap. Is that okay? So this was circulation density, am I right? Circulation density. Now it is what you call circulation. Now once you take dot product of this vector field, it is a circulation. Okay. Now look at here. Let me quickly explain one more part here. Okay. Suppose you have taken one closed what you call path integral. Okay. You have taken one closed path integral. Is that okay? What you do is, again you are going to do, so let me take it as P1 path integral 1. Okay, so let me take P1 v bar dot dl bar. Okay, now along with that one I'll take one more path. Is that okay? So I'll call this second path as P2. Is that okay? and I will add line integral P2 to this one, V bar dot dl bar. Okay. Now what is the effect? So to take this path integral, okay, I have taken it like this. To take this path integral, I have taken it like this. So this common part, line integral got cancelled. Isn't it? Just like earlier, surface integral got cancelled in the common part. Speak out. So when I do that one, what will happen is that okay? As a whole, okay, you get line integral of a vector field along this path. Are you grabbing this logic? Speak out. Because dl vector, okay. Let me just draw them separately. Okay. Let me just draw them separately. Then let me join. Okay. So this was P1, this was P2. Okay. Now let me join them. When you join these two, this line integral takes dl vector upward. This line integral takes dl vector downward. Okay. When you join these two, what will happen is, okay. So this is for P1. So this is for P2, isn't it? Speak out. This is for P2. And if you add the line integral, this part of the line integral vanishes, okay? As a total, you are finding the line integral of this path. That's not P1 plus P2. There's some other path, isn't it? Can I write like this, P? Is that okay? Now this is the path P. Speak out. Like that, if I do, I can make this one bigger and bigger and bigger, isn't it? Is that okay? Now look at here. Is that okay? I hope you got the logic. Very similar to earlier. Now you have a surface. Okay? You have a surface. Is that okay? You have a surface. Let me take a infinitesimal path integral. Let me take them anti-clockwise like this. Okay. So that my dA vector will be like this. Is that okay? If I take path integral like this, dA vector will be like this. Am I right? It will what you call generate a what you call area, isn't it? dA vector. Okay. I have taken this one over the surface. This is my big surface. Okay. Open surface. This surface is open, not closed surface. Okay. Now I'll take one what you call integral. Okay. I call that, let's look at here, del dA1. Okay. Del cross V dA1 dot dA1. Is that okay? Like that, I will take one more. So let me draw a little bigger, but you should take it as infinitesimal. Okay. Is that okay? So your dA vector is like this, dA1. So let me again generate like this. Like this. Whatever, just I got the idea, I'm just explaining, okay? I mean, everyone gets the idea after teaching sometime, okay? Maybe if you will find these things in some book. That's what I'm saying, okay? So dA vector like this. Now this part is cancelled. Okay, now what I do is I'm going to add this one actually plus. So del cross V, okay, dot dA1 vector, okay, plus del cross V dot dA2 vector plus again like that I do. Okay, let me take only 2. Is that okay? So then that will become, okay, that is equal to, what is this one? This is so can I say P1 closed integral of V bar dot dA bar, isn't it? Plus let me call this as P2 V bar dot dA bar. So, but again, left hand side is like this, you are adding like this, okay? The right hand side is addition of line integrals, okay? Line integral of the what you call paths which are joined together, am I right? That closed paths are joined together, okay? And I'm going to generate a surface like this. I'm going to extend everywhere, okay? So that I can generate the whole surface. So right hand side is, look at here, this was the closed path, okay? That was this path, am I right? Speak out. That was with this path. Oh, again, the boundary path, am I right? Of the surface. Can I take that like this? This is dA1, dA2. This path corresponds to dA1 plus dA2. That's the best idea. This path corresponds to, again, you generate a surface with dA1 and dA2, okay? Total surface. This path is a boundary line of that dA1 plus dA2. Isn't it? So V bar dot y dl bar, it should be dl bar. Tell me. Path integral, am I right? dl bar, V bar dot dl bar, pick out path integral. BK, path integral, right hand side. I am just taking this statement. Is that okay? Now if you do the same thing, take it as infinitesimal, because these are point operations, okay? Take it as infinitesimal and do the same thing throughout the surface area, okay? So then what will happen? This will become an integral. If you keep on adding infinitesimal of these things, that will become a, what you call, surface integral, am I right? And this will again, so, and take the total surface, and this addition of this path integral, that will become a total path integral at that, and that path is a boundary line of the surface. Okay, where I have taken like this. Yeah, now look at here. Now look at here. So shall I rub it out? I hope you got the point, how to generate the open surface using this one. So left hand side is adding, am I right? That is a surface integral of del cross V, okay, dot dA vector, okay, surface integral over this surface. You have taken small patch, you have taken dot product, you have integrated, okay. So that is equivalent to adding that small what you call, circulations, where there what you call common what you call path, effect of line integral around common paths getting cancelled, this kind of common paths, isn't it? Those effects are getting cancelled. As a total, that's equal to closed path integral of the total boundary, okay, total boundary. So this is the path integral, okay, that path is a boundary line of the surface here, is that okay, of V bar dot dl bar. What is this one? This is your famous Stokes theorem or fundamental theorem of curl. Speak out, try to generate the logic. Open surface integral, remember, you can't do this one for closed surface integral. For closed surface, there will be no path. What is the closed surface integral? 0. Isn't it? Look at the right hand side. For closed surface, if you shrink this path to 0, then right hand side is 0. Look at here. Speak out. When you see this right hand side, you can see that it is independent of the surface chosen. Am I right? Look at the right hand side. Right hand side depends only on this path. Am I right? If you choose a different surface with the same boundary, isn't it? Then left hand side remains the same. That's why curl of a vector field is a special class of vector field whose surface integral is independent. Exactly similar to this statement or this statement. Am I right? This statement. I did. Am I right? It was independent of the path chosen. Exactly the same statement you can do here. Look at the right hand side properly. It depends on the path, not on what is the surface whose boundary is this path, isn't it? So third one, that is surface integral of curl of a vector field, open surface integral of a curl of a vector field dot dA vector, okay, that is equal to, where path is the boundary line of the surface, okay, this surface, okay, where this surface was a boundary of this volume, am I right? In this case. Now this path is boundary of this open surface. So path integral, closed line integral of V bar dot dl bar. Can you compare now? Now to experience this one, you should do some problem. Apply this one, okay? You might have taken some closed path integral yesterday, am I right? I have given some examples, okay? So suppose I think I have given one of the example as I remember. Okay, one of the example that I gave, that was, I think, so there was a path like this from here to here and here, like this, am I right? So that was xy plane, am I right? Let me just give the hint to the problem, okay? You have taken this kind of path of some vector field, am I right? V bar dot dl bar, so closed path integral, am I right? You have taken right hand side already. Now, what you call, take the surface integral, okay? Take the surface integral over this surface. While taking the surface integral, how do you run x and y? I mean, again, now you have to take the surface integral. Now, which surface you choose? This is the boundary, am I right? I have given the boundary. You can choose any surface, am I right? Choose the simplest surface, this plane itself. Because I told, when you see the right hand side, this is independent of the surface chosen for a given boundary line, isn't it? Just like by seeing the right hand side, we have we said that it is independent of the path, isn't it? Exactly similar. Is that okay? Now again, what is the dA vector for this surface? That is like this. If this path integral is like this, okay, path integral runs along your finger, okay, your thumb will represent dA vector direction, x cap, y cap, that is z cap direction actually. Then definitely you can take v bar dot dA bar, okay, so that dA bar you can take, so like this, am I right? That's equal to dx into dy into z cap, am I right? And you can take curl of this vector field, sorry, not v bar dot dA bar, but this one curl of the vector field dot dA bar, am I right? Speak out. Curl of the vector field dot dA bar, am I right? Take dA bar like this, and while doing that surface integral, don't run this from, suppose if it is 0 to 1, don't run it from 0 to 1, 0 to 1. If you run from 0 to 1, 0 to 1, you will span the square region, not triangle region. You should know how to run the limit. That's what I have explained. Once you convert that one into two variable integration, okay, this will be converted into two variable integration after you take dot product, am I right? So I have shown how to do this triangular kind of shaped surface integral, okay? In case of that volume integral, yesterday's video that I have uploaded, I have given some idea, okay? If you are not convinced with that one, no, I mean, you have to do like this actually. You have to take it like this. You have to take it like this. Then you have to run something. So grab the idea how to run the limit, okay? And you try to show the equivalence. Or you do one thing, again, if you want to work out that this kind of integral later, you do one thing, okay? You take what you call closed surface line, so what you call your closed line integral like this. That's what Griffiths has given actually. Initially concentrate on the theorem, okay? Later work out that mathematics. Look at here. Do the closed line integral like this. Not a triangle. Speak out. Look at here. Now what you call, you take a surface like this. Then while doing this what you call surface integral, you can run x from 0 to 1, y from 0 to 1. Okay, if it is a square. First try to prove this theorem, or try to check out whether this, try to verify the theorem. Is that okay? Not proof. Try to verify the theorem, okay, using some example. For that you take a simple square, don't take triangular, because triangular, if you take that surface integral, limits would be quite tricky, isn't it? For square it is not tricky. X is going from 0 to 1, y is going from 0 to 1. You can quickly verify. So that is given in the Griffiths, okay? But you should know, if your path integral is like this, dA vector is like this, x and y like this, z vector is like this, am I right? That's why this is dA vector, this is area, dx into dy, okay? dA vector is like this. Again, this dA vector is fixed by right hand thumb rule in this one. Is that okay? Is that okay? So here this dA vector, this is a surface integral. Here this dA vector is outward from the surface. I hope you know that one. Close the surface integral. dA vector is outward from the surface. Okay? Yeah. Find the similarity. Look at here. This will happen for any scalar field. This will happen for any vector field. This will happen for any vector field. Okay? Curl of a vector field is a special class of vector field whose surface integral is independent of the surface for a given boundary line. Look at the right hand side. Right hand side depends only on the boundary line. then left hand side should also depend only on the boundary line. That means you can take any surface for a given boundary line, isn't it? Find the difference. Okay, solve as much problem as possible. Okay, if you solve all problems from Griffiths, that would be better. Now look at here. Quickly take these two statements, then we shall close this session. We have to go somewhere. Del cross V dot dA, okay, is open surface integral, okay, is independent of the surface, or it depends only on the boundary, right? Like this, it depends only on the boundary. Is that okay? It depends only on the boundary, not on a particular surface used for a boundary. Is that okay? I hope you got that one from the last statement. Okay. And if you make it as a closed surface, what will happen? So just to take it take it as a balloon. Okay. So in case of balloon, again if you tie that one, there will be again that balloon will become closed surface. Am I right? If you make that surface closed, there will be no path. That means this part is 0. That's why closed surface integral of curl of a vector field for whatever the vector field you take, okay, these two are true, dot dA vector is equal to 0 for any closed surface, because there will be no boundary line for a closed surface, or boundary line or boundary path will be shrink to 0. You can take that kind of idea, isn't it? If you shrink you make that what you call boundary smaller, and just like you are tying the what you call balloon, that will be 0.